Okay, so hi everybody. So I'm gonna try something new this time, which is I'm gonna live stream the video to YouTube. And so somebody suggested in the feedback that if we do this, then you can go back and look at previous parts of the lecture. So I've posted the YouTube link in the chat. And yeah, let's see how it works. I mean, worst case, it'll just record the lecture. So, okay. Let me share my screen. Okay. So, oops. So this is lecture 12. Okay. And today we're going to do three things. Let me darken the color. Yeah, okay. We're going to talk a bit more about induction and strong induction. And then we're going to talk about a closely related concept called recursive definitions, which is a new way to define functions. And then finally, we're briefly going to discuss the related concept of recursive algorithms. And all this stuff is the content of section 5.3, roughly. So okay, so last time, what did we say about induction? Well, so we basically introduced two new inference rules. So we had ordinary induction, which was prove some base case P of B. So given a propositional function, P of n, where n is a positive integer. In ordinary induction, we saw that if you prove P of B for some base case B, and then you prove that for every integer greater than or equal to B, P of K implies P of K plus 1, then the conclusion is that for every integer greater than or equal to B, P of n holds. This is ordinary induction. And then we also discussed strong induction, which is a variation of this, where you prove P of B, and then you prove this slightly different implication, which is assuming that the proposition is true for all integers between the base case and K. This implies P of K plus 1. And then the conclusion again was the same. So again, this is called the base case. And this is called the inductive step. So I want to make one remark. So at the end of so it's very important how you choose this propositional function P of n. So the remark is that at the very end of the last lecture, we tried to prove the uniqueness part of the fundamental theorem of algebra. So we managed to show the existence part, but we also tried to prove the uniqueness part using induction. And in particular, we tried to do this. Sorry, I don't know what's going on with my spelling. First, we tried to do this by induction, where P of n is a proposition. The integer n has a unique prime factorization. And this actually didn't work. This didn't work out. That was how the last lecture ended. But that's not to say that there's no way to prove this statement using induction. There is a way to prove this using induction, but you have to do induction not on the value of the number, but on the number of prime factors. So an alternate way to set this up is to consider the statement P of n is every integer m with, or I guess it has to be bigger than 1. So let's say bigger than 1. With, or let's write it this way, which can be expressed as a product of n primes. Has a unique prime factorization. Okay, so this is a different way to do induction, where now n is not the number itself, but the number of prime factors. And this actually can be made to work. So I'm not going to do it in this lecture, but if you reread the proof of the uniqueness part of the fundamental theorem of algebra using the well-ordering principle, you'll see that it's essentially showing you how to do a proof by induction based on this kind of propositional function. Okay, and okay, good. So any questions about this? Okay, so let's do one more. Let's do a few more interesting examples of proofs by induction. So here's a fun example, which is based on a puzzle, or it's based on a game. So here's something I'm going to call the splitting game. So the splitting game with n boxes. So how is this game defined? So you start with one, right? I think in the book it's described in terms of stones. So let's call them stones. So you start with one pile of n stones. So, okay, my stones are just going to be boxes. So here's, for example, here are 7 stones. And now in this game, what you do is you repeatedly split the pile into subpiles. So split a pile of m stones into 2 piles of r and s stones, where m is equal to r plus s. So this is a fancy way of saying, I have one pile right now. I'm going to split this into 2 piles. So I don't know, somebody want to throw out a way to do that?
Pile 3 and 4.
3 and 4. Okay, good. So let's split over here. Actually, I don't want to use such a thick marker. Let me reduce the thickness. Okay. So let's split here. So this is my first split. Okay. And when you do a split, you get points. And the number of points you get is the product of the sizes of the two subpiles. Get R times S points. So for this splitting, the number of points you'd get is 3 times 4, which is 12. And now the game. Sorry, does somebody have a question?
Shouldn't be that n stones.
No, it should be M stone. Sorry. So, okay. So M could be any number such that there's a pile of that number. So before you do any splitting, there's only one pile of 7 stones. But now after the first splitting, there are 2 more piles, right? So here's one pile with M equals 3. And here's one pile with M equals 4. Does that make sense?
Yeah.
Okay, so now the game is you keep repeating. Repeat on the subpiles. So repeat on subpiles until all the piles have 1 stone. Okay, so that means, okay, now I get to do some more splitting. So my second split, I have 2 piles to choose from now. Okay, and again, the goal is to maximize the score. Okay, so right now I have 12 points for my first split. How should I choose my second split? My goal is to get as many points as possible, and the points are given by the product of the sizes of the subpiles.
Keep splitting it down the middle.
Keep splitting it down the middle. Okay, interesting. So, okay, so for this M equals 4 pile, that's, let's say this is split number 2. So then I get 2 times 2 points out of this. For this M equals 3 pile, it's not so clear what the middle is, but I'm guessing you mean maybe just do this. So now here I get 2 times 1 points. Okay, I'm still not done. I have 1, 2, 3, 4 piles left, but there's essentially only one way to end the game. So I split here. Here I get 1 times 1 point. I split here. I get 1 times 1 point. And my final split is here. I get 1 times 1 point. So this is one example of, this is, one round of the splitting game where I chose this order in which to do the splitting, and let's see what my total score is. Well, so I got 12 points on the first turn. I got 4 on the second turn. I got 2 on the third turn. I got 1 on the fourth turn, 1 on the fifth turn, 1 on the sixth turn. So my total score is 16, 18, 19, 20, 21. So any questions about the rules of the game? Okay, so now I want you to spend a minute and I want you to see if you can beat my score. So just pull out a piece of paper, draw 7 stones, and see if you can get more than 21 points. Okay, so it looks like a bunch of people got 21. Anybody get more than 21? Less than 21? Okay, so it looks like everybody's getting 21. And that's not an accident. So it's actually a theorem that you always get 21. It doesn't matter how you play this game, you always get 21. And now the reason why you always get 21 is actually not clear unless you consider not just the splitting game with 7 stones, but you consider all possible splitting games with n stones for every n simultaneously. So the general theorem that's true, which we'll now prove, is that let's put it this way. For every n greater than or equal to 1, every strategy. So by strategy, I mean choice of order of splittings. Every strategy for the n stone splitting game has score exactly n times n minus 1 divided by 2. So this is the theorem we'll prove. And a special case of this is n equals 7. Then the score is 7 divided times 6 divided by 2, which is 21. So we'll now prove this theorem by strong induction. Okay, so let's see the proof of this. So again, I need to specify what my P of n is. So let P of n be the proposition, the splitting game with n stones has, or let's actually introduce a notation. So let score of n be well, okay. Well, okay, no, we don't need this notation actually. It's fine. Okay, always has score n times n minus 1 over 2. So let's prove this by induction. Just need to add some more pages. Oh. Okay. Okay, so what's the base case? Well, if n equals 1, the score is how many, you can't split it, right? So you don't get any points. Or yeah, let's just write it like this. Score equals 1, which equals 0. Which is 1 times 1 minus 1 divided by 2. So that's okay. And now let's do the inductive step. So assume k is an arbitrary integer greater than or equal to 1. And assume the inductive hypothesis, assume the inductive hypothesis, which says that the splitting game always has this score up to this value of k. So, and assume score of k equals k times k minus 1, or sorry, not k. Let's introduce a new variable. Score of I equals I times I minus 1 by 2 for all I going from 1 to k. Okay, so I guess I did end up using this notation score of I. This is the score of the splitting game. With I stones. And this makes sense because I've already proven that I mean this notation would not make sense if the score depended on the strategy, right? So this I'm only going to use score sub I when I know that that all games with I stones have the same score, and I do know that now because of the inductive hypothesis. Okay. So now I need to prove that the same is true for k plus 1. So consider the game with k plus 1 stones, and let the first split be that you split k plus 1 into r plus s. Right. So the first we haven't said which exactly split we do, but whatever it is, the first split looks like this, right? You split k plus 1 into two numbers r plus s, and we know that each of those is at least 1 and at most k. So I'm going to draw a picture here on the side. The picture here is that there's some number of stones. We don't know how many there are. There are k plus 1 of them. And however many there are, there is a first split. And it's going to split this into some r and s, where r plus s is k plus 1. Sorry, that's not a very good picture. Okay. So now, so what should I do now?
Well, you know that the score from k plus 1 is going to be rs plus score of r plus score of s.
Exactly. So the key point is after the first splitting, I now just have two different copies of the splitting game, but on smaller piles, right? Like the left-hand side is just another copy of the splitting game on R stones, and the right-hand side is a copy of the splitting game on S stones. So therefore, by the inductive hypothesis, so now notice that the score is RS, which is what you get for the first split, plus the score for the splitting game on the R stones. Okay, so score on, I guess, left pile plus the score on the right pile. And now, by the inductive hypothesis, since the left and right piles are smaller than k, this is rs plus r times r minus 1 over 2 plus s times s minus 1 over 2, which now we have to do a little bit of algebra. So this is 2rs plus r squared minus r plus s squared minus s over 2, which when the dust settles, turns out to be r plus s times r plus s minus 1, 2, which is k plus 1 times k divided by 2. Now, the beauty of this is this works regardless of what the first split is, right? It's independent of what r and s were. This is always true. So that's it. We proved pk plus 1. So this completes the inductive step.
Wait, don't you mean r plus s times r plus s plus 1?
Oh, well, let's see. Okay, let's just do the algebra here. So this quantity is r plus s squared minus r plus s. So I think what I wrote is correct, actually.
Wait, but that would be k times k minus 1.
R plus S
Oh.
is K plus 1. So R plus
I
S
see, I see, I
minus
see.
Never
1
mind.
will be K.
Okay.
Right. Yeah. So the point was that r plus s is actually k plus 1. Maybe that was your confusion. Yeah. Okay. So, the point I want to highlight about this is in order to understand the game on 7 stones, you really need to broaden your viewpoint and study the game on n stones. I don't know any easy way to prove this with just some fixed number of stones. You really need to study all the games together so you can do induction. And the second thing I want to emphasize is that induction is commonly actually used to analyze games, to analyze strategies for games. So the previous examples were all things involving numbers. I'm doing this to emphasize that you can use induction to analyze other processes. And the inductive step usually involves, like, the key property of this game, so that allowed us to do induction, is that after one step, the game splits into 2 copies of the same game, but on smaller number of stones. So any questions about this proof? Okay. So now I want to I want to make some remarks about how to visualize what's going on with induction. Many people have been sort of wondering about this in office hours. So let me mention 2 different ways of visualizing what induction is achieving. Okay. So 2 ways of thinking about induction. So the first is what I think of as the bottom-up way. And here, what is induction doing for us? Well, it's saying that suppose you have proofs. So given proofs of P1, P2, all the way up to PK. The inductive step tells us how to get a proof of PK plus 1. Okay, so you can view this as, like, really induction is telling us how to generate an infinite sequence of proofs in a systematic way with this particular structure. Then the second way, which is different, so this is like this notion of climbing up the ladder. The second way, which is called top down. so these aren't quotes because they're not mathematically well-defined terms, is it's answering the following question. So given the task of proving, so not given the proof. So suppose I ask you to prove pk plus 1. The inductive step reduces this to the task of proving pk. Okay. So the difference here is I'm viewing it as I'm breaking down a complicated statement into a simpler one. Whereas in the bottom-up view, I'm saying I'm combining a bunch of simple proofs into a more complicated one. Now, these are both correct ways of thinking about induction. They're just different perspectives that might help you understand why it works and what's really going on. Okay. Any questions or comments about this? Okay. So now I want to move on to a related topic, which is recursive definitions of functions. And in particular, I want to say that the book also talks about recursive definitions of sets. We're going to skip that for now. Okay, so what's the goal here? The goal is how do we define a function from, let's say, the non-negative integers to the positive integers? Or I guess this is not a question mark. So the familiar way that you're used to of doing this is you just state an explicit formula. For example, you define a function as f of n equals n squared. So you say exactly what is the rule mapping the input to the output. But there's a more flexible way of defining functions that comes up a lot, especially in computer science. So here's a new way, which is called a recursive definition. And this consists of two ingredients, just like a proof by induction. There's a basis step. And the basis step is just to define some finite number of values of f, the first few. So define f of 0, f of 1, all the way up to f of b for some finite b, some finite integer b. So I only defined a small piece of the function. And now there's an inductive, well, it's usually called a recursive step. Recursive actually just means the same thing as inductive, except it's usually used when talking about definitions, and it's used to emphasize this top-down view, but it's really the same meaning as inductive. I'll say a little bit more about what that meaning is in a moment. The recursive step is for every integer that's bigger than b, you define f of k plus 1 in terms of all the smaller values of f. Okay. And the conceptual point here, the important thing is that these are smaller values of the input. Okay. So let's look at an example of a recursive definition, which really is a fundamentally different way of defining a function from the familiar way, because you don't just specify it in one shot. You're kind of specifying it piece by piece, slowly, but in this very specific order. So let me show you an example. It's kind of a famous example. So here's one example. This example is the Fibonacci numbers. And we so the Fibonacci numbers are a sequence. So they're a function traditionally defined as a function from non-negative integers to positive integers. This union 0 is not a big deal. It's just there because conventionally this is how we define Fibonacci numbers. So what's the base? Did I call it the base case? Or basis step is what I called it. So let me continue to call it that. Basis step. So I'm going to define f of 0 to be 1 and f of 1 also to be 1. So in this case, b, what's the value of little b in this recursive definition?
1.
1, yeah. So I've defined f of 0 and f of 1. And now the inductive or recursive step, I suppose, to be consistent with the book. So for the recursive step, I'm going to say if k is at least 2, or I guess if k is at least 1, define f of k plus 1 to be f of k plus f of k minus 1. Okay, now this is a, so maybe you should ask yourself, why is this a valid definition? And let's just look at an example of the, let me first just compute a few values to show you why it's a valid definition. So the function, if I were to list the values of the function in a sequence, then the base case tells me what the first two values are. Okay, so this is what the base case is doing. And then for any future value, I apply the inductive step to compute it as a function of the previous two values, right? So I just add up the previous two values. And this is being done by the recursive step in the definition. So now f of 3, well, it's the sum of f of 2 and f of 1, so it's 3. F of 4 is 5. F of 5 is 8, and so on. And the reason this is a valid definition is that any f of n eventually appears on this list. Right? So this is indeed a rule that uniquely gives me an element of the codomain for every element of the domain. So it's a function. It's a valid function definition. So any questions about this example? So I mean, I want you to ask yourselves this question: why is this not a circular definition, right? So is this a circular definition? It seems that we're defining Fibonacci numbers in terms of themselves. We're defining Fibonacci numbers in terms of other Fibonacci numbers. Why is this not circular?
Well, it's always increasing.
Okay. Yeah. Can you be a little bit more precise?
The sum of two non-negative integers will be greater than their components. So there isn't a point in the function that it turns around and start to decrease.
Oh, okay. So that's not the reason. So we would actually be fine even if the function decreased. I mean, for example, let's look at another example.
Wait, do we always have to start from f of 0, or can we also start from like f of 1?
Well, according to this, you can start. I mean, okay, right now I've done everything with 0. Yeah, if you're defining a function on a different domain, you could start from, the smallest element of that domain. In this case, that happens to be 0, so we have to start from 0 because we have to define f of 0, right? Because it's a function. But okay, so it's actually not related to the fact that the function is increasing. The reason it's not circular, it's because every function value f of k plus 1 is defined in terms of function values on strictly smaller integers. Okay, so I mean like f of I for some I strictly less than k plus 1. That's why it's not circular. I mean, to show you what would be a circular or what would be a sort of, we're never defining f of k plus 1 in terms of itself. We're always defining it in terms of things we've already defined. So actually, maybe let me show you an example of an invalid inductive definition. It's to say, okay, f of 0 is equal to 1. F of 1 is, I don't know, equal to 1. And f of k plus 1 is equal to I don't know, f of k plus 2 plus f of k plus 3. Okay. Now this is not a valid recursive definition. Why is that? What property fails?
They are smaller values.
Yeah, you're trying to define k plus 1 in terms of bigger values. And it's totally unclear how this is going to work, right? Because f of 1 is 1, fine. F of 2 is 1. Oh, sorry, f of 0 is 1, f of 1 is 1. F of 2 is defined in terms of f of 3 and f of 4. But we haven't even defined those yet. So what is this? We don't know. So the whole content is that we're doing this and we're sorting the elements of the domain in increasing order and defining the function in that order. Okay, so these types of definitions come up a lot. I mean, you can define all sorts of interesting sequences. Here's another example. you can define f of 0 is 1, and f of k plus 1 is square root of 1 plus f of k. Okay, so this is like 1 square root of 2, square root of 1 plus square root of 2, square root of 1 plus square root of 1 plus square root of 2, etc., etc. So it's kind of, you know, a pain to write out a formula for this. Actually, it's not clear to me how to do that. But this is a perfectly valid definition of a function on the non-negative integers. Okay, so the reason this is relevant in this chapter is that these kinds of definitions come up a lot, and induction is perfectly suited to proving things about recursively defined functions. Okay, so let's say so what do recursive definitions do? Well, recursive definitions specify f of k plus 1 in terms of the previous values. So they're particularly suited for inductive proofs. So let me now prove an interesting statement about the Fibonacci numbers. So here's a theorem. Well, okay, here's a definition. So this is a definition due to, I guess, the ancient Greeks. So you can ask, if you have a line segment, what's the way to divide it into two parts, A and B? So you want to find A and B positive numbers such that the ratio of the two parts, so A over B, is equal to the ratio of the length of the whole interval to the largest part. Okay, so this is something that was considered, I guess, thousands of years ago. And the answer to this, as you might know, is, well, let's solve this, right? So solve for x equals A over B. You get x equals 1 plus 1 over x. That's a quadratic equation. So if you multiply everything by x, you get x squared minus x minus 1 equals 0. And if you solve this, you get x equals 1 plus or minus square root 5 over 2. And we know x is positive. And so A over B is this number, the golden ratio, 1 plus 5 over 2. Okay, so what we're going to prove, so okay, this number has all sorts of aesthetic significance. You know, people have used it in various parts of science, art, architecture, etc. But it actually has something nice to do with the Fibonacci numbers, which is not obvious. And so I'm now going to prove this theorem that the Fibonacci numbers, so we looked at a few of them earlier, seem to be getting bigger. And there's this question of how fast do they grow? We're going to prove by induction that they grow at least as fast as powers of the golden ratio. Okay, so here's a theorem. If n is at least 3, then so by the way, this golden ratio, this number is about 1.6 something. So in the Fibonacci numbers, we have 1, 1, 2, 3, 5, etc., etc. And the claim is going to be if n is bigger than 3, then I guess n plus first Fibonacci number, f of n, is at least, let's give this number a name, let's call this number phi, is at least phi to the n minus 2. Okay. So any questions about this statement before we begin to prove it? Let me just double check that 3 starts at 3 and not at 2. I don't want to mess this up. Yeah, okay. Actually, when n is bigger than 2 is good enough here. And wait, am I off by 1 here? Let me just check this. Okay, let's just prove the weaker statement. That'll be certainly easier. Okay, so now we'll prove this by induction. Okay, so there's going to be a base case, a basis step, and in the basis step, a priori, it looks like we just have to prove this for n equals 3, right? So P3 says that f of 3. So what's f of 3? F of 3 is 3. Sorry, I think, let me prove this slightly different statement. Let me say if n is greater than or equal to 2. So this is one annoying thing about proofs by induction. Sometimes there's some confusion about it's called an off by 1 error, that sometimes it's very easy to make a mistake where you're off by 1. But let's see if this works. If it doesn't, we'll change it. So okay, so the basis step is, so P of 2 is the statement that f of 2 is bigger than phi. And f of 2 is just the number 2. And 2 is bigger than 1.618. So this is true. Okay. And now let's start doing the inductive step. So there's actually, I've actually already deliberately made a mistake. So notice that in the definition of the Fibonacci numbers, the next number is defined in terms of the previous 2 numbers. So if I just start the induction at if I just start the induction at 3, that's not going to work, because f of 3 is expressed in terms of f of 2 and f of 1. So what I need to do is I need to actually include p of 3 in the base case. So this is that f of 3 is bigger than phi squared, which is that 3 is bigger than 1.618 squared, which is true. This is also true. So now in the inductive step, what am I going to do? I'm going to assume k is some integer bigger than 3. And now I'm going to assume that f of I is less than phi, or sorry, greater than or equal to phi to the I minus 1 for I going from 3, 4, all the way up to k. So this is the inductive hypothesis now. Now, the reason I have these two numbers in the base case is because of the definition of the Fibonacci sequence. I need to know the previous two numbers in order to know the next one. So now, okay, so observe that f of k plus 1 is equal to f of k plus f of k minus 1. Why is that? That's the recursive definition.
Wait, are you using the exponent as I minus 1 or I minus 2? Because in the problem you said I minus 1.
Oh, sorry,
okay.
I changed it to 1. I'm sorry, I changed it to 1 in the middle. I was using a slightly different convention than the book. The book is starting from 1. I'm starting from 0. So, yeah. Okay. So now, okay, so now the recursive definition, the beauty is that it expresses fk plus 1 in terms of smaller fk's. And so now, what should I do in the next step?
We can now use the inductive hypothesis to say it's greater than or equal to phi to the k minus 1 plus phi to the k minus.
Exactly. So I'm going to apply the inductive hypothesis to each of these things. So I'm using strong induction, right? So f of k is bigger than phi to the k minus 1 plus, and this is bigger than phi to the k minus 2. And this is by the inductive hypothesis. And now my goal is to show that this is bigger than phi to the k, right? So I don't know, how do I relate this to phi to the k?
Maybe try factoring out phi to the k minus 1.
Okay, so this is equal to phi to the k minus 2, maybe you mean, times phi plus 1. Right? Now I want to prove that that's phi to the k. And this is where the golden ratio comes in. How is the golden ratio defined? Well, it's a solution to this quadratic equation, right? So if you plug in phi into this, what this implies is that phi squared is equal to 1 plus phi. That's the defining property of the golden ratio. But that's exactly what we need in this proof here. Right? This is equal to phi to the k minus 2 times phi squared by the quadratic equation. And this is just phi to the k. Okay, and that's it. So this completes the induction. So p of k plus 1 holds as desired. Okay. Now we should take a moment to reflect. What would happen if I tried to prove that f of k is at least alpha to the k minus 1 for some number that's bigger than phi? I mean, just what would happen to this proof?
It isn't going to work anymore, I believe, because then you're going to have, I think if you've got alpha greater than phi, you're probably going to have alpha plus 1 is less than alpha squared.
Yeah, so another way to put it is that phi is the largest number with the property. So phi is the largest number such that phi to the k minus 1 plus phi to the k minus 2 is bigger than phi to the k for every is bigger than phi to the k for every k bigger than, I guess, 2. And so you couldn't prove this with a higher number. And that's why the golden ratio appears in this proof. You can also show that actually, as k gets larger, this bound becomes tight, but we won't do that in this class. So actually the ratio of consecutive, so we won't prove this yet. We might prove it after the midterm remark. The limit, I know calculus is not a prerequisite for this course, but the limit of this quantity is phi, actually. We won't prove this for now, but so actually this exactly tells you as k gets large, the sequence literally just grows as powers of, approximately as powers of the golden ratio. Okay, so that's an example of a proof by induction using a recursive definition. And the recursive definition just lends itself beautifully to this kind of proof because, you know, it's made for this. It expresses pk plus 1 in terms of smaller pk's. So any questions about this? Okay, and just as, you know, another remark which is easy to show, so it's you can fairly easily show that f of k is at most 2 to the k. And maybe you should do this as a homework exercise, just to get some rough ballpark on the rate at which these numbers grow. So it's between golden ratio to the k and 2 to the k. Okay, so now, lastly, I want to briefly talk about recursive algorithms. So a recursive algorithm is very much like a recursive definition of a function. In that a recursive algorithm solves a problem by reducing it to a smaller instance of the same problem. Okay, so this is a very top-down view of describing what a recursive algorithm is. And we've already actually seen a recursive algorithm in this course, namely the Euclidean algorithm. Okay, so recall, so how does the Euclidean algorithm work? So GCD of A and B, where A is strictly bigger than B and both are non-negative. Now, I'm going to rewrite the algorithm in a way that's really a recursive definition of a function. Okay, so here's the recursive definition. So first I'm going to define the domain of the function. So let S be the set of all pairs A comma B such that A is bigger than B and B is bigger than 0 and all of them are integers. Or I guess they could be, yeah, okay, just integers. I already said they're non-negative. So this is the set of possible inputs to the Euclidean algorithm. So now I'm going to define a function EA, which stands for Euclidean algorithm, going from the set S to the set of positive integers as follows, recursively. So what's the basis step? Well, the basis step is that Euclidean algorithm applied to any number comma 0 is just 0. If you ask me the GCD of a number and 0, I just output the number. I just output, oh, sorry, A, not 0, A. Yeah, A. And now we have a recursive step. Which is that, how do I define what the Euclidean algorithm does to a pair AB where B is not 0? So let me put that as a condition. So if B is positive, then the Euclidean algorithm applied to A comma B is just the Euclidean algorithm applied.
Are you writing something? Sorry.
Yeah, can you not see?
No. Oh, wait. Now I can. Yeah.
Okay, great. Yeah, I was very happy. I reinstalled Windows and did a bunch of stuff and did a lot of tests, and I thought my screen wasn't going to crash, and it looks like it hasn't. So, okay. Okay, so if B is positive, then what did we say that you do in the Euclidean algorithm? Well, you replace, you're instead of computing the GCD of A and B, you compute the GCD of B and A mod B. But remember that this A mod B equals this remainder R when you express A as BQ plus R in the division algorithm, right? Okay. Now, this is not quite in the same vein as the recursive definitions we looked at earlier, because it's got two variables, right? We talked about recursive definitions for functions of the integers, but here, there are now two variables. So why is this a reasonable definition? Well, can anyone say?
We know that A mod B is going to be strictly less than B, which means that, like, if we keep applying this, we're going to get a strictly decreasing sequence of integers in our second entry, and any strictly decreasing sequence of non-negative integers eventually hits 0.
Yeah, so that's a very precise formal explanation of why this is well defined. But there's a picture associated with this, which is that the base case, so there's this big set S. It's not a very good picture of S. And the base case first defines EA on pairs that look like this. So that's what the base case does when the second coordinate is 0. But now the recursive step then defines the function on pairs where the second coordinate is 1. Right? Because if you apply the recursive definition to a pair where the second number is 1, then A mod 1 is always going to be 0. But now once you know what the function looks like here, you can also get the function on all tuples where the second coordinate is 2. Why? Because when you take the remainder mod 2, it's going to fall into one of these categories. and so on, if you repeat this process, right? So this is well defined because A mod B is always strictly less than B and is always non-negative. So this is an example of a recursive function definition on a set that's not the integers. But really, if you follow what's happening in the second coordinate, it's the same principle. And this is a recursive algorithm. There are two ways of viewing this. It's a definition of a function, or it's actually a, you could write this down in a computer and run it, and it would do something, right? So, I mean, recursive algorithms are really the same thing as recursive function definitions, except the interpretation is that, well, it's an algorithm, so you're computing something. You're computing the output given the input. But algorithms are functions anyway. And so what's the actual computation that would happen if you tried to implement this on a computer?
It would keep applying the recursive step until you eventually reach something that looks like the basis step.
Yeah, but really, in terms of the actual arithmetic that the computer would be doing, it would be this, right? This is the division algorithm. Sorry, I don't know why that came out in a different color. Okay, so now I'm going to prove finally rigorously that this actually computes a GCD. We never rigorously proved that because we didn't have a framework to write proofs about things like this, but now we do. So let's state this as a theorem. Theorem is if you have any pair of integers in the set S, then if you run this recursive algorithm, you actually get the GCD. Okay, this is not obvious, right? Because the left-hand side is a recursively defined function, and the right-hand side is defined in some completely different way, right? You look at all the divisors and you take the largest common divisor. So let's prove this by strong induction. So now, I'm going to do, again, it's very important to know what you are doing the induction on. It's a little tricky here because there are pairs. But what, as you run the algorithm, what number is going down?
The right one?
The second coordinate, right? So maybe we should do induction on the second coordinate, right? So let P of n be that the Euclidean algorithm applied to AB equals GCD AB whenever the second number is at most n.
Can you also just say that you're inducting on B? Does that work? Or do you have to say it in the proposition?
Yeah, you're right. Yeah, sure. Yeah, you could just say by induction on B. So you don't always have to write this proposition. I'm just doing it to be very, very pedagogical. So by induction, yeah. So sort of more maybe sophisticated way to write it is by induction on B. So now, okay, what's the base case? Base case is that EA of A comma 0 is that for every A, that's, I guess, at least one, EA A comma 0 is equal to GCD A comma 0. And this is true because EA of A comma 0 is A, right? So I won't belabor this. And again, why is A at least 1 here? So implicitly in this Pn, there's a so there's a whenever A is bigger than 1 and B is less than A. Right? Because the domain of the algorithm, the set of inputs of the algorithm, consists of integers A comma B, where A is strictly bigger than B and B is greater than or equal to 0. So A has to be at least 1. Okay, so now what about the inductive step? Okay, so we need to so assume B is equal to K plus 1. So we need to show that assume B is equal to K plus 1 and A is just any number bigger than 1. So we will show that this Euclidean algorithm applied to A comma B is equal to the GCD. Okay, so now observe that the Euclidean algorithm applied to A comma B, well, what does it do? Well, according to the recursive step, the definition in the recursive definition, it just applies Euclidean algorithm to B of A mod B. So this is the recursive definition. Okay, now what do I do? Well, A mod B is strictly less than B. So by the inductive hypothesis, this is equal to GCD of B comma A mod B. The reason for this is the inductive hypothesis. But now I want to show that this is equal to GCD of A comma B. But I already did that in like lecture 5. That was the starting point of the, how we derived this algorithm. This is equal to GCD of A comma B. This is, I think, there in lecture maybe 6, maybe lecture 7. Yeah. But now I'm done. Right? I just showed that the Euclidean algorithm computes the GCD. Okay. So any questions about this proof? It's a little tricky because there are these two coordinates. The key thing to remember is what are we doing induction on? We're doing it on the second number here, B, because that's the thing that goes down. I mean, okay, in principle, I guess the first one goes down too, but it's easier to do it this way. So any questions about this?
Professor, what's the word after by induction? Proof by induction.
It says on B.
Okay.
Yeah, so that means that the thing we're doing induction on really is B. I mean, P of n is really saying we're doing strong induction on B. And implicitly in here, I'm assuming the inductive hypothesis, right? Okay, so that's all I want to say about this. I want to make some remarks about the exam, since that's something maybe everybody has thought about. So, okay, what do I want to say about the exam? So first of all, I think people did pretty well. So 75, the median was 75. I think that's pretty good. That's higher than the usual median on the first exam for this class by a lot. So don't feel bad if your numerical score isn't very high. The other thing I want to say is don't worry too much about your grade right now. So we're not following the usual high school grading scale where 60 is failing and things like that. So, like maybe the thing I want to say is this class is not curved. So what that means is that there's no limit on how many on the number of A's, etc. So you're not competing with each other to get a decent grade in this class. Just focus on demonstrating to me that you have learned how to write proofs and understand what's going on. So don't worry too much about your grade if you see a low number. And we're replacing the lower midterm by the second one anyway. The second thing I want to say is that it's okay to be struggling with writing proofs. Okay, so just think back to when you learned how to write essays in high school. The first time you wrote them, they weren't perfect, right? Unlike just learning how to apply a formula, it is something that you learn by practice. So don't feel like there's something wrong if you're struggling with the writing aspect. The last thing I want to say is that in the feedback form, a lot of people are reporting feeling isolated, like feeling quite alone in the class because everything is on Zoom. So again, I just want to reiterate, please go on the Discord, please find people to study with, find people to explain the material to, and to discuss it with, and to maybe work on the homework with. That'll be a much more enjoyable experience for everybody. So try to work in groups on the homework. Yeah, okay, I think that's it for now. Yeah, okay, so I guess that's the lecture.
Hi, Professor.
Oh, hi.
Can I talk to you privately for a little bit?
Sure, let me just see if any other people have questions.
Yeah, me too. I also want to talk about like a few things in person.
Okay.
Yeah.